Hey guys, this is your trainer Anirudh Chhillar. So we are back with one more video that's on OSPF, Open Shortest Path First. So in OSPF itself is a link state routing protocol, and we have a concept of area in the OSPF. So what we do basically, we put routers inside the OSPF area in a single area of OSPF. That's how we reduce the routing information on each and every router. So how we can achieve that with other functionality as well of the OSPF? Let's go guys.
So let's start this OSPF now. Open shortest path first. The very first thing about OSPF is that it is a link state routing protocol, and I hope you understand very well that what are the differences in between distance routing protocols and link state routing protocols. There are some differences, actually key differences, like in distance routing protocol we saw that routers were not having a complete topological database table. In ASRP it was not possible. The only information that they were having inside their topology table that was given by their neighbors. Because in distance vector routing protocol there is a rule in which, according to that, routers will always advertise only and only best route information towards their neighbors. Understand what I mean to say? In ASRP, in RIP, in IGRP, only and only best route information will be advertised towards their neighbors. That is why it is not possible for them, for routers to have a complete topological database table, right? But in link state it's not like that. Here concept is completely different from distance vector routing protocol. If we talk about the link state routing protocol, as I have already discussed it with you, that link state routing protocols will always maintain a complete topological database. Here in link state routing protocols we do not have that rule in which, like we were saying, that okay, only best route information will be advertised towards their neighbors. Here in link state that rule does not work. Actually, here in OSPF, whenever two devices will form OSPF neighborship, are you getting my point? Whenever two OSPF speaking routers will form neighborship, then they will exchange their database table, not their routing table, not their best routes. Try to understand, in OSPF they do not exchange only and only those routes which are available inside their routing table. They do not exchange any information which they have inside their routing table. They exchange only that information which they have inside their database table. So when OSPF neighborship will come up in between two OSPF speaking routers, then they will be responsible to exchange their OSPF database only. Have you understood it?
Yeah.
Tell me. So this is the biggest difference in between distance vector routing protocol and the link state routing protocol. And because all routers will maintain an identical database, an identical copy of database table, right? Because in link state, if we talk about link state routing protocols, they will always maintain a common database. On all routers you will always find a common database. But if we talk about this OSPF particularly, then in OSPF we are also having the concept of areas. So this rule works only for a dedicated area. Like for an example, if you are having 10 routers within a same area, within a single area, then on all those 10 routers you will always find common database. Understood? Fine. Now because we are saying that okay, all routers would maintain a complete database or a common database, and in all link state routing protocols we have an algorithm which is known as or you can also call it SPF algorithm, discussed algorithm, or you can call it SPF algorithm, shortest path first algorithm. Now, when a router maintains a complete topological database on all that, on that topological database sparsely, like for an example, your router has maintained a topological database now, and now then OSPF will run SPF algorithm onto that existing database, and from that existing database it will pull some best routes and will install them into its routing table, or you can say it will create SPT, shortest path tree, and then further it will install best routes inside its own routing table, right? So in OSPF there is no chance for formation of routing loops, because all routers will maintain a complete topological database, and all routers will define their best path, best route by themselves. For best path election, for best route election, OSPF, or you can say linked state routing protocols, will never depend only on, will never depend on their neighbors. Previously in ESGRP and RIP, what was happening, that if neighbor was saying that okay, the cost, the metric to reach this particular destination is this for me, so in that case we were required to accept that information, or it was mandatory for routers to accept that information, and it was mandatory for router to take decision based on that information given by their neighbors. But here in OSPF, because all routers will maintain a complete database separately, so they will define their best path, best route separately. They will not be depending on any, try to understand, they will not be depending on any other router, on any neighbor for their best path selection, right? So all routers will define their best path separately, so there will not be any chance for the formation of routing loop. I hope you have understood it, right? So now, so this is the basic algorithm, or this was really basic of OSPF, that how does it really work. So the main difference in between distance vector and this linked state routing protocol is, like, distance vector will never maintain a complete topological database and hop count value was always there, but in OSPF you do not, in OSPF all routers will keep a complete topological database, as well as there is no process, there is no concept of hop count values. It means that if you are having a huge number of devices in your network, then you can implement OSPF over there, because there will not be any problems like we had in RIP or in ESGRP, because in ESGRP maximum hop count value is what, 255. However, by default it was 100, right? So if any prefix is coming after crossing more than 100 hops, then by default your device will drop all those prefixes. But further you can configure your hop count value as to up to 255. But at last I can say that there was some limitation in ESGRP2, right? That was maximum up to 255. But in OSPF, remember that hop count value will never be carried forward within the OSPF updates. Inside routing table, you will never come to know that okay, this is, this network or this destination is connected, or this network, this destination network is located after crossing this or that number, after crossing that number of hop count or that number of hops, right? So there is nothing like hop count value in OSPF. Okay, the next thing is, like as I said in ESGRP, that it is distance vector, and here like OSPF is coming under linked state routing protocol. So accordingly we are also having differences in their AD values as well. Like the AD value of ESGRP is different as compared to OSPF. Like in OSPF we are having default AD value as and 110, right? So default AD value of OSPF is 110, and here in OSPF for different types of routes you do not have different types of AD values. Are you getting my point? So because in OSPF, like you can have 3 types of routes probably, like inter-area, as well as external. So for all types of routes, its default AD value will remain as 110. It's not like EIGRP. In EIGRP, for internal prefixes, its AD value was 90, and for external it was 170. So in OSPF, for all types of prefixes, we are having a same AD value, which is 110, right? Second thing, if we talk about this OSPF particularly now, so in OSPF, you must remember that it uses IP protocol number 89. It means it will also hand over its payload directly to IP. It will also hand over its payload directly to IP. It will not hand over its payload to any other protocol like either TCP or UDP. Like RIP was using UDP, but OSPF do not use either TCP or UDP. It will directly hand over its packet to the IP. That's why it is having protocol number 89. Then next thing is like OSPF will be using some multicast not some, actually two multicast addresses, two different multicast addresses for transmitting its messages, like 224.0.5, and also it will use, sometimes it can also use .6. The meaning by .5 is what? For all routers, for all routers, and .6 means for so if you want to send some information, if you want to send some updates in the direction of DR only, then you will be using .6, and if you want to send your information for all routers, whether it is DR or BDR or DR other, in that case it will be using .5. Fine. Next thing, you must remember that OSPF is a completely or fully classless routing protocol. Like it can support contiguous and discontiguous network both. Are you getting my point?
Yes.
By default. So OSPF is a classless routing protocol and will support contiguous, discontiguous network, both of them. It's not like EIGRP. In EIGRP by default auto summarization was enabled, and due to that auto summarization, EIGRP was supporting and only contiguous networks. But after disabling auto summarization, then it started, EIGRP also started to support contiguous as well as discontiguous networks. Fine. So it will always support contiguous as well as discontiguous networks. Fine. Now let's talk about that. What are the requirements to form OSPF? First, area ID must match. Second, tell me what process ID? Timers must match. Hello and dead intervals. Timers must match. Then next, authentication. Fourth, subnet mask must match. Fourth, Stub flag must match. Apart from it, like a stub flag must, that's true. MTU size must match. However, we can override this rule in OSPF, right? We can override this rule, but I'll let you know that why is it necessary or in which conditions we can override this rule, right? Seventh, router ID must not match. Router ID must not match. Anything else? Sometimes what happens that network types will get mismatched. So in that case also might be that they will not form neighborship. So network type is, I'm not saying that network type must match. I'm saying that network type should match. Because in some conditions they can form neighborship even their network type is different, but in some cases they will not form neighborship, right? So I will let you know later on that in which conditions they can form neighborship even their network types are mismatching, and in some conditions they can also form neighborship even their network type will mismatch. Are you getting my point or not? So I'll be discussing it with you that what is the meaning by network type here and all these things. So here in OSPF we do not have something like k value, that is why here nothing like k value, right? Here is we are having only and only like area ID, then we are having timers, authentication is there, subnet mask is there, stub flag is there, MTU is there. Router ID must not match, network type should match. It's not mandatory that okay it must match, but because in some conditions of course it is mandatory that okay it must match, but in some conditions it will not be mandatory actually to match it. I will let you know. However, it must match because even like for an example, you have configured two different network types on both ends and they have formed a neighborship, but still they will not be able to exchange their routes with each other, right? So they can form neighborship, but still they will not exchange their routes information with each other. You understand what I mean to say? So finally you have to match your network types, but at least they can form neighborship. That is why I said that network type should match. Fine. So all these requirements must be fulfilled before going to configure OSPF in between two neighbors, in between two routers. Fine. Apart from it, now let's talk about types of packets available in OSPF. You understand what I mean to say? Types of packets. Like we were also having types of packets in EICRP2 and we learned them like hello, update, query, acknowledgement, reply. Do you remember in EICRP, right? So today we are going to learn these types of packets in OSPF as well. So if we take an example of OSPF, then here also we are having five different types of packets available in OSPF. So first one is what? Hello packet. Acknowledgement. Update. And reply. It was in EICRP, right? And if you talk about the OSPF here, hello, DBD, LSR, then and finally so like we were having five types of packets available in EICRP, but in EICRP we were also having two other types of packets too, like SIA query and SIA reply. So forget about that, but in OSPF we are having only these 5 types of packets only. And now in OSPF this hello will be known as type 1 packet, DBD will be known as type 2 packet, LSR will be known as type 3 packet, LSU will be known as type 4 packet, LSAC will be known as type 5 packet.
It's like output.
Yes. So inside the field of the packet, if type 1 is specified, it means it is containing hello packet, and if it is containing type 2, it means it is containing DBD. And what is the full form of DBD? Database descriptor. So I hope that all of you are remember the full forms of all these packets. LSR is link state request, LSU is what? Link state, and LSAC is what? Link state. Good. Now all these types of packets are having different tasks. Like, first of all, I'll teach you all these things in very brief. Like hellos will be used by OSPF just to discover a neighbor and to maintain neighborship. And these hello packets will be generated by OSPF periodically. Sometimes, I mean, in some cases it will send these hello packets in every 10 seconds, but in some cases it can also send these hello packets in every 30 seconds as well. So it will be depending on network type. Understood? Let me tell you once again. OSPF will be using these hello packets just to discover its neighbors and also to maintain neighborship. That is the only uses of hello packet here in OSPF. And in some cases hello interval will be 10 seconds, and in some cases hello interval will also be 30 seconds. Type 2, which is known as DBD, database descriptor. Fine. As per its name, database descriptor. What does it mean? That it will be responsible to describe your database. It will simply describe you. It will provide you description of database. A small description. It will not provide you database. It will provide you only description. That's why its full form is database description or descriptor. Database descriptor. Have you understood it or not? So basically the uses of DBD is something like this. For an example, if you are having 2 different routers now, and if they are going to form neighborship with each other, then they will send, I mean, before giving an update to each other, first of all they will send DBD to each other. Like R1 will tell to R2 that okay, I am having these things in my database. I'm having these routes in my database. It will inform to R2, and in same manner R2 will also inform to its neighbor R1 that I am also having these routes in my database. Now if R1 came to know that okay, I mean if R1 come to know that I am not having, let's say R1 have received DBD from R2, it means R1 have came to know that what exactly routes are available in the routing table of or in the database table of R2. Now R1 will compare its own database table with the database of R2. If it find that okay, there is something missing, then R1 will ask to its neighbor R2 that okay, I don't have this information, please provide it to me. Are you getting my point or not? In same manner R1 will also give its DBD to R2. So R2 will also compare its own database with the database of R1, and in case if R2 comes to know that okay, I'm not having this particular information, so now R2 will ask to its neighbor for that particular information only. So this is the uses of DBD. Have you understood it or not? Database descriptor. So it will provide only and only description. It will not keep, or it will never tell about the database. It will tell about, I mean it will provide only and only description, nothing else. Second, LSR, linked state request. Let's say that they have exchanged DBD packets with each other. After exchanging DBD packets, now they came to know, R1 came to know it is having some sort of information. It is not having some prefixes. So for those prefixes only, for those updates only, now R1 will send a request to R2. For that purpose, we are having here LSR, linked state requests. In that message, actually router will send a request to its neighbor that I need this information only. So for that purpose, we are having here LSR. Then LSU, linked state update. When a router receives a linked state request, then it will check its own database, and if it finds that okay, I'm having this information in my own database, then it will be responsible to provide LSU, linked state update. In linked state update, actual information, actual database will be given or will be carried by LSU, right? Actual database, actual information will be carried by LSU only, linked state update only. Understood? And when a router receives LSU, linked state update, means if a router has received any update packet from its neighbor, I get my point? If a router has received update from its neighbor, then it has to send an acknowledgement back into the response of LSU, linked state update. Are you getting my point or not? It has to send linked state acknowledgement in the response of LSU, linked state update, just to inform to sender that okay, I have received the information that was given by you. Hello? Yes, because this LSU have very importance or very important role in OSPF, because here OSPF do not use TCP. So in case if your update gets lost somewhere in the network, then there will not be any retransmission because you do not use TCP. So there must be some external acknowledgement for it, for these type of packets, right? So for LSU only, inside OSPF we are having an external acknowledgement. So there is a rule in OSPF that whenever you will receive any LSU linked state update, then you have to provide a linked state acknowledgement in the response of linked state update. So whoever will send LSU, it must receive linked state acknowledgement from the receiver, right? And if it does not, if sender do not receive LSAC back from the receiver, it will retransmit your linked state update. And it will keep on to retransmit your linked state update till it gets linked state acknowledgement. It's not EIGRP. Here it will keep on to send you update.
So R2 will wait for the acknowledgement. There will be any timer to...
Exactly, and that is by default. Like retransmission timer is by default 5 seconds. So if you do not get an acknowledgement within 5 seconds, then it will retransmit your update. This is a retransmission time, retransmission interval, right? Understood? Any problem? Tell me. Fine. This was the brief introduction about all those packet types here in OSPF. Now, remember that all these types of packets of OSPF will also be encapsulated by 24 bytes long OSPF header itself. Or you can say that there will be a common 24 bytes long information that will always encapsulate your all types of packets. And that information is called OSPF header. Remember, whatever I'm going to specify inside OSPF header will be same for all types of packets. Means that OSPF header will always encapsulate your all types of packet, whether it is hello, DBD, LSR, LSU or LSAC. And remember that here By default, it will send multicast packets, but if you configure your neighbor statically here in OSPF, because this is also possible in OSPF to configure your neighbor statically. So if you have configured your neighbor statically in OSPF, then it will send only and only unicast messages. But if you do not configure your neighbor statically, then it will send multicast messages. Understood? Have you understood it or not?
Yes, sir.
Fine. And as I said that there will be a 24 bytes long common information which will always be responsible to encapsulate each type of packet, whether it is hello, DBD, LSR, LSU or LSI. Now problem is like, or question is like, in those 24 bytes what kind of information we are having actually.
All types.
Like version, type, area ID, you understand? And apart from it, let me show you. Just wait for a moment. This is OSPF packet format. Just try to understand. There are 5 distinct, means different types, different OSPF packet types, right? All OSPF packet type begin with a standard 20 byte long header, means common 24 byte long header, right? So that's what I said, that all packets will be encapsulated by those common 24 bytes, right? This header is described first. Each packet type is then described in the succeeding section. And one more thing, the decision that whether this packet should be accepted for further process or not will be taken by looking at first 24 bytes only, by looking at OSPF header only. Because if there is any problem, then it can find it within those first 24 bytes. And if it finds any problem, within first 24 bytes, then it will never accept that packet for further processing. Like if your authentication gets failed, will your neighborship move in any state? If your router ID matches, will your neighborship move into any state? If your timers mismatches, then will your neighborship move into any state? If your area ID mismatches, will your neighborship move into any state? You know why? Because those hello packets will not be accepted for further processing. So you see, every OSPF packet starts with standard 24 bytes. This header contains all the information necessary to determine whether the packet should be accepted for further processing or not. This determination is described in this. You see, version is there, type is there, packet length is there, router ID is there, area ID is there, checksum is there, authentication type and authentication data. So if, like for an example, type has mismatched, however type will not mismatch, version can mismatch. So if your version mismatches, then also your packets will not be accepted for further processing. And if your router ID is also same on 2 different neighbors or on 2 different routers, then also packets coming from neighbor devices will not be accepted for further processing. Area ID, if area ID mismatches, because area ID must match for neighborship, right? So if area ID mismatches, then also your packet will not be accepted for further processing. Checksum is also there. Checksum will be used for you can say loop avoidance, or you can say security here. Here inside this OSPF header, checksum will be used. Checksum will be used for security reasons only, kind of hash value, right? The next is what? Authentication type. And you know very well that OSPF supports multiple types of authentication, such as null, type 1, type 0, type 1, type 2. And now OSPF version 3 have also started to support SHA authentication. So we will also configure SHA authentication, but right now it will be good for us to discuss only type 0, type 1 and type 2 only, like null, plain text or MD5. Fine. Authentication data is also there, and then these 24 bytes will always be common for all types of packets. In these first 24 bytes, nothing will get changed throughout all packets. So all packets will always be encapsulated by these 24 bytes, these common 24 bytes. You see version, OSPF version, this is specification documents version 2 of the protocol. Type field is there. Type means, as you know that we are having 5 types of packets, type 1, type 2, type 3, type 4, type 5. If 1 is there, it means we are having hello in this. If it is 2, it means we are having DBD. If it is 3, we are having LSR. If it is 4, it means LSU. And if it is 5, then it means acknowledgement. So like type 1, 2, 3, 4, 5. 1 hello, 2 is database description, 3 request, 4 update, 5th acknowledgement. Packet length checksum, the standard IP checksum of the entire contents of the packet, starting with the OSPF packet header but excluding the 64 authentication field. This checksum is calculated as the 16-bit ones complement of ones complement sum of all the 16-bit words in the packet excepting the authentication field. If the packet's length is not an integral number of 16-bit words, the packet is padded with a byte of 0 before checksumming. The checksum is considered to be part of the packet authentication procedure. For some authentication type, the checksum calculation is. So finally, we can say that checksum is also used by OSPF for security purposes. That's the only uses of checksum having here inside OSPF, right? So this is the uses of checksum. Then authentication type, as you know that we are having various types of authentication, and then authentication data. So that's all about your OSPF header. So these 24 bytes will always be common for all types of packets in OSPF. Then further, as I said, that hello packet is there, and if you talk about the hello packet, I have already described it to you that okay, hello packets are OSPF type 1 packet. These packets are sent periodically on all interfaces, including, however, this is, in Cisco devices, it will exclude virtual link. By default, it is not gonna to send periodic hello packets over virtual link. In order to establish and maintain neighbor relationship. So what I told you about hello packets, I defined in same manner, right? So this is all about the hello packet. Then after it, these are the contents of hello packet, and up to here, see up to here, these 24 bytes will be common. This is your OSPF header, and preceding section would belong to your hello packet. However, this entire packet will be known as hello packet. But in this hello packet, first 24 bytes will remain same. Then after, as I said, that network mask, subnet mask must match. So subnet mask is part of hello packet. So once they will exchange their hello packet with each other, it means they will also exchange their subnet mask information too. So in case if their subnet mask do not match, will they form neighborship? No. Hello interval is there. Router priority is also there. Now you know very well that why do we have hello interval here, as well as dead interval is also there. So hello interval, dead interval, both of them are there. So both types of timers must match. Then router priority is also there. So router priority would be in use during the election of DR and BDR, and also master and slave. Do you remember that in OSPF during adjacency states, I will also teach you that there will be an election of master and slave, and that election can be done based on their router priority. Router dead interval, I have already told you, DR designated router. So if you have elected any router as a designated router, so whenever a designated router will generate a hello packet, it will always mention its own router ID under designated router. Hello? I mean not router ID, actually the IP address of that DR interface. And one more thing, DR is not your router. Your router is not DR. Actually the interface of your router is DR. This is the interface state. Like, I mean when we say that okay, this is DR, BDR or DR other, so these all are states of the interface in OSPF. Backup designated router, so if you are having BDR, then also it will specify that this is your BDR. And then this is what? Neighbor. I mean this is neighbor's router ID. The meaning by this neighbor field is what? Neighbor's router ID. Neighbor's router ID. So I will teach you that what is the actual uses of this neighbor router ID inside hello packet. But yeah, it's true that it is mandatory to have neighbor's router ID. Fine. So these are the contents of hello packet. And if you go to DBD, again first 24 bytes will remain same. And this preceding section will come from DBD. So MTU information is going within DBD packets. Some fields are also there to define that okay, whether it is master or slave. For that purpose we are having here MS bit. M bit is for more bit. I is for initial number or initial DBD. As you can see, I init bit. When set to 1, this packet is the first in the sequence of database description packet. And M bit, more bit means it is also having some more DBD packets to transmit. MS bit will define master and slave. If it is 1, it means this is master. If it is 0, it means it is a slave. And I'll be teaching you that what is the role of master and slave here. So these all are the components of DBD packet. And you can see that finally it is having this DD sequence number as well. I'll teach you that okay, what is the role of this DD sequence number. But first of all, before going to understand it, we have to understand all other things, and then during practicals I'll teach you that what is the role of this DD sequence number. I mean along with practicals I'll make you understand that okay, this is the role of this sequence number and this is the role of this and LSA header. So see, this is not containing entire LSA. Inside DBD it is not taking entire LSA. It is having only and only LSA header. Are you not getting my point? See, as I said, that in DBD you will never contain a complete information. So that has proved now that in DBD you will be having only and only LSA header, not complete information. And after having LSA header, we can at least confirm that whether this LSA is available in my database table or not by just looking at its header. That is why in DBD they will send LSA headers to each other. I will also teach you that what is the meaning by LSA in OSPF, link state advertisement. Even I will also teach you that how many types of LSAs we have in OSPF. Understood or not? Fine. Then next is going to be link state request. So first 24 bytes will again remain same from here to here. And then after ls type, link state ID, advertising router. This information will also go along with, because in LSR it will poll to its neighbor. It will poll to its neighbor that okay, please give me this information only. So it has to provide some information to get that information. That okay, I just want it to get this information only. That is why sender will send ls type, link state ID and advertising router. That okay, the LSA advertised by this router only, I want that LSA only which is advertised by this router only, which is having this link ID and this type of LSA. So this information would be contained by LSR. Finally LSU. First 24 bytes will be same up to here, and then after you can see that LSAs are there. Entire LSA. This time it is not containing LSA header. Whereas DBD was having LSA headers only, but this time it is containing entire LSA. That is why I said that a complete information will be given by LSU only, or LSU will be responsible to contain a complete information, not DBD. DBD have only description. Link state acknowledgement. First 24 bytes will again remain same, and LSA header in acknowledgement. Let's say I have received one LSA. I have to give an acknowledgement back to the sender, so I will send only that LSA's header into that, so that whenever a sender will receive this LSAC, in that it will find LSA header, and in LSA header it will find that appropriate information, that information by which it can confirm that it can get confirmation that okay, that LSA has been delivered onto destination, onto neighbor. Have you understood it or not? So
complete a singular acknowledgement message for all LSAs, like LSU.
for one LSU there will be one LSAC. Now in one LSU you can have multiple LSAs as well. Understood? So this is all about types of packets. I will also explain it to you in more details, but during practicals only I will capture all these packets and then I will show you that okay, this is the information, this is the uses of it.
Okay, so that's the end of today's video. So I hope you learned something new today. We'll be coming with few more videos of OSPF, guys. See you later. Thank you.